All right, what if we could build a brain, not from flesh and blood, but from pure logic and probability? Well, that's exactly what we're going to explore today as we dive into the fascinating world of Bayesian networks.
So here's the big question, right? How can a machine reason like we do, make smart guesses when it doesn't have all the facts? The answer is this really powerful idea called probabilistic reasoning, and it is the engine that makes these networks tick.
Okay, first up, let's get the core philosophy down. We're going to explore the fundamental concept that lets our artificial brain navigate a world that is, let's be honest, rarely black and white.
So unlike traditional logic, which kind of demands absolute certainty, probabilistic reasoning is all about likelihood. It's about weighing possibilities to find the most plausible conclusion. I mean, it's a lot like how we make decisions every single day, right? Using our own judgment and a whole lot of incomplete information.
Now that we've got the philosophy, let's look at the anatomy of our thinking machine. We're going to start with the network's blueprint, the static structure that holds all of its knowledge.
The most basic pieces here are called nodes. You can think of them like the neurons in our artificial brain. Each node represents some variable that has a level of uncertainty to it. Things like, will it rain today? Or is the sprinkler on?
So how do we connect these neurons? Well, we build something called a directed acyclic graph, or a DAG for short. It's simple, really. You place your nodes, you draw arrows to show which things influence other things, and, this is super important, you make sure there are no loops. This gives you a clear, one-way flow of influence.
Once you build this graph, what you have is the joint probability distribution. Just think of this as the network's complete worldview. That term probabilistic entanglement, it just means it's a map of how everything is interconnected, how a change in one spot ripples out and affects the likelihood of everything else, even before it gets any new info.
So we have the blueprint, this kind of static map of the world. But a map isn't the same as the journey, is it? So how does this brain actually think? Let's dive into the dynamic part, how it learns from new data and updates what it believes.
The whole thinking process is really about updating beliefs. So the network starts with a prior belief, its initial world model. Then it sees new data, we call that evidence, and it updates its model based on that. That, in a nutshell, is how it learns.
And the result of all this learning? That's the posterior probability. It's the network's new, more refined belief. It's this powerful combination of what it expected to see and what it actually observed in the real world.
And how does this update physically happen? It's through a process called belief propagation. So when new evidence hits one of the nodes, it doesn't just stay there. It ripples through the whole network like a wave, causing every connected node to update its own beliefs until the entire system settles on a new, coherent understanding of things.
But wait, this network can do so much more than just update beliefs. Now we're getting to its most advanced tricks, where it moves from simple learning to a much, much deeper level of understanding.
Okay, this is a massive leap. You see, most AI sees correlation. It knows that two things often happen together. But a Bayesian network, it can actually achieve causal inference. It can start to understand why one thing causes another. And that is a profound shift in machine intelligence.
And what's really, truly incredible is that the network doesn't even need us to give it the blueprint. Through something called structured learning, it can just analyze a pile of raw data and figure out the most likely causal connections all on its own. It's basically performing the scientific method to build its own model of the world. Just amazing.
So, at the end of the day, why does building an artificial brain like this really matter? Let's talk about the real-world implications, not just for AI researchers, but for all of us.
The real power of these networks, especially their causal abilities, leads us right to causal explainability. And that is the ability for an AI to not just give you an answer, but to actually explain its reasoning, to tell you why.
This is what gets us away from that whole black box AI problem, where we have no idea how it reaches its conclusions. With explainability, we can actually audit these systems, we can understand their logic, and most importantly, we can start to build a genuine foundation of trust. And that leaves us with one last pretty profound question. As AI learns to explain itself, the challenge really shifts. It's no longer just about building a thinking machine. It's about how we, as a society, are going to choose to interact with it, to rely on it, and ultimately, to trust it.